Hello everyone, my name is Daniel Café. I'm a professor at the University of Brasilia in Brazil. I currently teach courses of embedded electronics such as electronic system design and embedded software development. In the last 2 years I've been working on nanosatellite development, such as development of printed circuit boards for the CubeSat standard and development of software, embedded software for onboard computers. So today I'm going to talk a little bit about what are the best practices and what are the challenges that we face when we write software for this kind of system. So today's topic, I've used the title Software Development for Critical Systems, in the case, a specific case of CubeSats, because CubeSats, once they're launched, there is no longer there's no way to do system maintenance. You cannot have access to it manually because it's in orbit. So you have to develop your software thinking about that. How will you manage and how you maintain the software that's running on a satellite? So for the agenda, I would like first, I've separated this talk in different parts. So I'm gonna do a quick overview of what are the challenges and what are the problems that we face when developing software for nanosatellites. And I'm going to show some suggestions on how to correct and minimize those problems. Then I've chosen some selected features that I think are the most important ones to know about, and they are the base to understand this level of programming that we're going to use. So I'm going to talk a little bit about timers, which is important to track time and to measure time as well. I'm going to talk about interrupts and specifically about low power modes, which is very important when you have a system that is powered by batteries, because we need to develop the system with power efficiency in mind. And then I'm going to end this talk speaking a little bit about the different programming models that we have and how to choose among them. So, when you develop a satellite, there are some things that we must be aware of. When the satellite is launched and when the vehicle that is carrying the satellite launches the vehicle into orbit, it reaches the speed that is going to orbit, but at the same time, the satellite doesn't stay still. It rotates around its own axis. So the satellite has more or less a trajectory like this. So this effect that makes the satellite rotate, it's called tumbling. And sometimes it's necessary to remove that rotation, and that process we call detumbling. So the detumbling sometimes isn't necessary, and it can save you some bucks, can save you some money when you develop simple systems. In simple projects, we just choose omnidirectional antennas so that we don't have to worry about rotation and stuff. But in other projects, for example, when the orbit distance, the radius is very low, very high, we have to use directional antennas to make the communication link more efficient, and we have to point that antenna to the ground station. So there must be a mechanism to turn and rotate the satellite. There are many ways to do that, with inertial wheels, with magnetic actuation, or even with electronic propulsion. But this is not the focus of the topic. I'm going to talk about what are the problems that are introduced to the communication system when you have tumbling, when the satellite's tumbling. So sometimes you will have the satellite pointing directly to the ground station. So in that case, you have a great link. A communication link is very powerful and you have a great communication window. But when the satellite rotates, there are some cases in some positions that's not the case. And the link is weak and sometimes you don't have link at all. So you cannot communicate as well as before. In that case, you have to compensate that with some other techniques, some software techniques to compensate that effect. So here's an idea. During a satellite communication, we expect packet loss, okay? On the downlink, we expect more than 10% of packet loss. This is from previous experiments with satellites already in orbit. But the problem is not so much the downlink, but also the uplink. The uplink is very problematic. So amateur radio frequencies are very polluted and it's very hard to get the message up in the sky. It would be very easy to send commands, to send information, send data bytes if you are, like, for instance, in a boat in the middle of the ocean and you can communicate very well. But if that's not the case and you are in a city, it's very hard to communicate because there is a lot of interference. So we expect more than 40% packet loss during the uplink process, during the link channel, the communication channel on the upside. So here's an idea. You might think, like, for instance, there are some applications that are mostly focused on imaging. So the satellite gets images from the Earth or from experiments inside the satellite and sends those images back to Earth. So that's the information that you need to get. Sometimes the information will get through, but sometimes it won't. And sometimes the worst is that part of the information will be corrupted. So, like, for instance, if you receive an image, part of the image will be corrupted, so you cannot recognize the image, but the other parts are okay. So you might think, well, a very efficient way to solve these problems, maybe do a second request to the satellite to send me just the chunk or the part that has been broken, that has been corrupted by interference or somewhat. So in that case, indeed, it is very efficient because you're not occupying the bandwidth as much as you would if you download the whole image again. But the problem is, since uplink is very hard to get, it's very hard to send commands to the satellite. So another strategy, which is simpler and solves the problem as well, is downloading data twice. So if you have a chunk of data that you want to obtain from the satellite, request or write your software thinking that you are going to send it twice to the Earth. Because if you get two images, which are the same image, but the first image gets corrupted here on the upper side and the other image is corrupted on the bottom side, you can combine those two images and recompose and recreate the totality of the image without corruption. This is somewhat slower and less efficient than sending just the chunk that was corrupted, but from the system perspective, from the whole, it is faster because if you keep trying to get those chunks of images one by one, it's gonna take longer. And when the satellite, like for instance low orbit satellites that have very short windows of time to communicate, when you're trying to get the data, the satellite is already gone. So the best thing is when you get a connection, enjoy it and make it worth it, just downloading data twice. So another recommendation, so to think about when writing satellite software, is to use a beacon. So in the satellite will emit a beacon. Let's say for every 10 seconds it will emit a beacon with very short informations. Like for instance, its own name, some telemetry like temperature of the solar panels, the capacity of the battery and stuff like that. But you should include in that beacon information an index. Like for example, the number of commands that were received. Because when you send a command, and with very simple protocols, you don't have an acknowledgement from the satellite. You will not know if the satellite has received or not your message or your command. So it's very interesting to see if your message was received. So if you try to send a command or try to communicate with the satellite and the satellite's not responding. So you wait 10 seconds and you check the beacon data to see if the command counter has incremented by 1. If it has, it means that the satellite has successfully received your message. If not, it means that you have to send it again. So there is a clear compromise here between choosing the correct time interval of the beacon so that the communication is not so slow at a point that you just will lose the time window to communicate, but it cannot be so short as well. It cannot be too short, otherwise it will every beacon sent, every data sent will consume power from the battery of the satellite. So there is a clear compromise there. Since beacon data is so small, you can't use a 10-second interval, which is okay for retrieving communication errors from the ground. So that's an idea to minimize, not to solve, but to minimize the packet loss problem. Another interesting issue is when you face interference in space, like for example cosmic rays. So cosmic rays are harmless to living beings. This is a well-known issue in space, and cosmic rays don't have enough energy to change the behavior of living beings, with cells. But they can interfere with microelectronic circuits because they have enough energy to flip a bit inside a transistor. So they can flip the state of transistor or change the charge in a capacitor, which is very problematic in not in combinational circuits, but in sequential circuits, and more specifically in memories, such as ROMs and flash memory, where the data is stored in the memory in a non-volatile way, and you expect it not to change over time, but somehow that data will change because of cosmic rays. So that's a clear problem, and if that cosmic ray reaches the controller of the memory, it is possible that the controller will not respond until you reboot it. It's actually very funny, that joke that every time you call your ISP provider and say that you have a problem with your connection, the first thing that they will tell you is to reboot the router. So it's the same thing here, because they do that because that solves 90% or more of the problem. So we'll do the same here, because it's that kind of problem has a randomic behavior. You don't know when it's going to happen. So it's interesting to do a power cycle, that's what we call, do a power cycle every 24 to 48 hours, so every day or every 2 days, so that you can refresh your system. Since the systems like an onboard computer or a microcontroller, very simple microcontroller with a very specific software, they boot up very fast, a reboot is not very painful or is not very harmful to the system as a whole, because you can, for instance, schedule that reboot for a period of time that the satellite will not be orbiting on the visible window from the sky, from where you want to communicate. So you can easily synchronize the clock of the satellite with your clock and set up the reboot to be programmed in a window of time that you know that you're not going to transmit or receive anything. So more on that, but not very related to cosmic rays, more about memory management and stuff. Sometimes it's useful to use magic words to mark parts of the memory that will help you to find data. I don't know if you're aware of, but in your computer, for example, the bootloader, the software that comes before the operational system, it has a magical word that in your hard drive that will locate the start of the bootloader. And that's very interesting because when you do a memory dump and you collect data from the satellite and you collect data from the memory, you want it to be easy to locate your data. So visually you can actually locate where is that data. So that's very helpful. Another thing that you can actually use is always use and verify the bytes that you're sending. So include at the end of the transmission a verification code. I recommend using the CRC16 for large chunks of data. For small chunks of data, you can actually use CRC7 or 8 for only 7, 8, or 8 bits of parity. Why do I recommend this? Because it's actually a simple algorithm. If you have a hardware that doesn't have it implemented in a dedicated peripheral or implemented in hardware, you can easily write a software to implement CRC. It's basically a XOR and shift operation. Any CPU can handle that. But in any case, most CPUs have that already implemented in hardware, so it's easy to use. Why that is so important? Because you need to check if the data that you sent has been received correctly. So, for example, when you're downloading an image or things like that, it's interesting to know if all the bytes that you have sent are correct. If the CRC matches, so if the checksum adds up to 0 when you receive, it means that the bytes that you received are correct. And last, for this class of problems, an interesting approach here is to boot in safe mode every 1 or 2 boots. I mean, every day or two, do a safe boot. Why is that important? Sometimes when you are communicating with other peripherals, the microcontroller or the microprocessor of the onboard computer, which is one of the PCBs on the layout of the CubeSat, that chip, the processor, will communicate with other peripherals. Let's say the accelerometer, for instance, or temperature sensors of the solar panels, or getting data from the power system, for instance. So eventually the buses, the communicating buses, they block because some slave on the bus has eventually is broken or has received so much interference that it cannot continue to communicate. So when you try to access that interface or that bus, you will not be able to proceed in your software because the software will wait for a reply from the slave and the software will not continue. So we have to deal with that problem in different ways. One way is to boot in safe mode. So every time there is a peripheral that's not responding and it's blocking communication on a bus, you need to, so you will wait until the next reboot, and when the next reboot executes, you need to know what was the last boot. So it's interesting to save on the non-volatile memory a boot counter. So let's say every odd number you boot in safe mode, so that you can actually You will not initialize any peripheral outside of the onboard computer. You will only maintain communications with the radio to receive commands from the ground station. And in that safe mode, you should expect a initialize command from the ground. So there will be a magic word from the ground station saying that, okay, I know you are in safe mode now, so you can continue to boot up and initialize all peripherals. Because safe mode will always happen once in 2 days, but in the beginning of the satellite life, all the peripherals will be working fine. So you need a specific command from the ground to let the onboard computer run free. So this is an interesting idea, but another approach, which is actually more robust, I think, is to, whenever you try to access a bus, you should use a timer with a timeout. So if a peripheral doesn't respond or doesn't reply in a given amount of time, let's say in 3 seconds or in 5 seconds or in 1 day, you should give up and mark that peripheral as a broken peripheral or erroneous peripheral because it is blocking communication on the whole bus. So you should no longer try to communicate with that device. So it's also interesting to keep on the non-volatile memory, on the flash memory, or in a separate memory from the onboard computer. It's interesting to keep up a table whether the devices are working properly or not. And that information you can send back as a telemetry data back to the ground station. So that will be part of the telemetry data. So that's an interesting approach. Both approaches, boot in safe mode once every 2 boots and using timeout every time you access a bus, are not exclusive. So you can use both. So that's something to keep in mind. Finally, there are other things that you should think of when developing software for nanosatellites. There is, which is code maintenance. How do you maintain code over the years when the satellite is already in orbit? So you cannot go there, plug a cable and update the software, or you cannot run new codes. Everything that's spec'd on the satellite is already flying. So imagine if you send a satellite, the launch date is next week. So you have to finish your software, you wrap everything up, integrate, send the satellite, so you cannot have any more access to it, and you discover a bug. You have a replicate on your computer and you discover a bug. What do? So it's interesting to have a mechanism to manage and maintain the software that is already running in orbit. Those mechanisms have different meaning. Let me try to decompose them in different parts. So once the satellite is deployed, there is no way to do maintenance. One thing that we can do is do a software update over the air. Auto updates are quite challenging to do when you're working with a satellite, because it's hard to upload data. So you need to check the chunks of data, chunks of software. You have to compact them in small pieces and send them in small pieces, though, so that will take a long time to upload the whole code. Another challenge is that you will reserve part of the memory, part of the non-volatile memory for the new code that you want to update, and you need to split in 3 different parts. One for the code that is running, one for a backup plan, and one for the code that you want to update to. So your usable memory space will be reduced in 2/3, which can be very expressive in some missions. But the idea is, so you have 3 parts of code, they are very similar. the backup plan, the actual code, and the code that you want to update to. The code, there is a part of the code that will do the update, that will check the chunks of code to check the CRC is correct, and etc. Whenever you have a full updated version of the firmware on the satellite, you can replace the firmware directly into the code that is executing. But if you do that during execution, that will be a problem. So the interesting thing to do is have a small piece of code, which is a bootloader, that will recognize when it has to update. So you prepare in a table on the non-volatile memory, you say, okay, for the next boot, I want to update the code, and then you reboot. When you reboot, the bootloader will detect that change and will do the full code copy from one part to the other. And you need a magic word at the end to confirm that the copy was actually made. So the bootloader also has to check if the copy was made at the end. Because imagine if in the middle of the copy, in the middle of the update, you have a problem or there is a power cycle. If that happens, you will lose the code and the satellite will never boot up again. So the idea here is to verify that the code was actually updated, and if it was not fully updated, you then will boot to that backup plan, so that third part of the code, that's which is a backup code. And it can be very simple. It can be just a simple code just to receive more chunks of update firmware, and when it's completed, you then run and you execute the update. So it's quite tricky, but it's very recommended. So this should be very carefully designed in your system. Another approach, which is much simpler, is the code injection. Well, code injection is much simpler than full software update, because code injection allows you to send new functionality, so new functions, new parts of the code, a library, full library. You can send new data to the satellite and execute that new data, execute the new code that you send. So that's interesting. For instance, if you have a test that you want to do, but you didn't have time to code the tests when you were in ground. So if you have a code injection system, you can then send part of that executable code to your satellite, and there is a part of the memory which is reserved to that code. And the entry point will always be the address of a function. So you have to do that manually in your code. So whenever you want to execute the new code that was uploaded, you call that static function that you programmed. So it's interesting to have a radio command to execute a injected code. So that's a very practical way to do small updates. With code injection, you can actually program from the ground up, from the zero, a update over the air software. It's doable. So code injection is absolutely, I would say, it's required if you want to do code maintenance in your satellite. A third option here, which is more a debug tool and not so much a maintenance tool, is bus injection. So bus injection is another idea that you can use to debug or communicate directly to peripherals that are connected to a bus. So it's very important that from the ground you should be able to dump memory or write data to or read data from peripherals that are connected to the different buses of the system. Like for instance, an I2C bus or an UART link. So this is very important. So you should predict and you should program a radio command that will access any bus with a given number of bytes in two ways. So you must predict a command that will only do a write in a specific number of bytes, and a command that will do only a read within a specific number of bytes, and a third type of command that will do first a write and then a read, because that can be very practical too. So try to predict that, because that's very important to debug and actually to access peripherals from the ground. And then segment or a part of the solution of the bus injection solution is a memory dump. So it's important from the ground to get memory from anywhere of the system, not only from the onboard computer, but it's interesting that you do a dump of memory, like from this address, dump 256 bytes that I want to see what's inside the memory. So this is a very important command as well. So these are mostly the tips and hints that I want to give for a starter that's starting to develop code, a nanosatellite code or a onboard computer code, because these are most of the features that are essential for the success of a mission. So this is it for this video. I'm gonna upload another video. Now I will talk about timers, because counting time and that's mostly related to the previous section where I talked about timeout. So if you access a bus, it's interesting to have a timeout and never block your code. So in the next video, I'm going to talk a little bit of how do we program timers to use them as a timeout counters for bus accesses. So I see you guys in the next video.